Welcome back. Today we will start by checking your classwork homework from last night, which were the 13 problems on the bottom of page 7. Again, 8 and 9 were optional. When solving by elimination, these were a little bit harder. So if you wanted to try them, you could. Here are the answers. And you are just going to check over your work. You can pause this if you need to. Just so you know, on the bottom here, the very last row says 2 hours of TV and 1 hour of football. On this page, I just had some work that I had started in my class yesterday when I was going over this. And this is number 3, the equations that you would have needed to set up to solve this problem. If you let x equal the number of pens and y equal the number of pencils, we had a total of 6. So x plus y is 6. And then pens were $1 a piece, so 1 times x. And then pencils were 50 cents each, so 50 cents times y. And that total value would equal $4. So to have one equation that represents how many we have, and the second equation represents how much they cost. Also had been asked to set up number 7. So in number 7, to use elimination, we just lined up the equations. And in this case, we're just adding them together. X plus negative x cancels. 2y plus y is 3y, and negative 1 plus negative 8 is equal to negative 9, and then you solve from there. If you did try numbers 8 and 9, you needed to multiply one of the equations to make them cancel. So I chose to multiply the top equation by 2. That would allow this negative y to become negative 2y. So that 2y and negative 2y would cancel. But when you do that, you have to also multiply 2 times x and 2 times negative 4 to get the negative 8. And then you can combine. To get the y value here, you plug the x back into either equation and solve for y. To get the x value in this equation, you plug in the y value. Number 9 was the hardest, so if you did try that as a challenge, I chose to multiply this equation by 3 and this equation by negative 4. The reason is because if I multiply 4 times 3, I'm going to get positive 12. And if I multiply 3 by negative 4, I'm going to get negative 12. And having a positive 12 and negative 12y cancels. So if you have any questions about that, you're welcome to ask. Your other alternative to solve these all would be to solve them graphically. So if you had done that, you should have gotten the same solutions. All right, we're going to turn to page 8, and we are going to start looking at some different types of systems instead of linear. So you learned linear systems in Math 1, which was graphing or having 2 lines on the same graph, and then you're just looking for the point where they intersect. So you can solve systems involving quadratic equations using methods similar to the ones used to solve systems of linear equations. The points where the graphs of the equations intersect represent the solutions. So that's pretty important. You're always looking for the point where they intersect. With a linear equation, just to recall, I'm going to go back to the previous page. We could have one solution. You could have an infinite number of solutions because one line is on top of the other, or you can have no solution at all because the lines don't touch because they're parallel. With a system that has a quadratic and a linear, you're going to have a parabola and a line. So think of how you can draw a parabola and a line together so that they have two solutions. And then a parabola and a line where if they went on forever in both directions, so you have this window to look at, but if it went on forever, that it would only have one solution. And the same here is no solution. When you draw it, you have to imagine if the functions went on forever, that they would never ever touch. So if you start with just a parabola, I think it's easier to just get that on your graph and then go ahead and try and draw a line in there that meets this requirement. So a line where it will cross the parabola twice, a line where it will cross the parabola only once, and a line that will never cross the parabola. So here you could draw a horizontal line, a diagonal line, but as long as it touches twice, you're good. So there's your two intercepts. With one solution, I have seen students draw a vertical line, kind of like a vertical line test would cross once, or a horizontal line that crosses through the vertex. And that line isn't perfectly horizontal. Even if it were slanted a little bit, that would be okay. It could also slant right along the edge here and touch once on the side. We call that drawing a line tangent to a curve, when it just brushes up against the curve and touches once. So that, or if you had drawn a vertical. No solution at all. I've seen students do something like this, and that isn't going to work. That's wrong, because if these continue to move upward, eventually they'll cross. But drawing a horizontal line at the bottom under the parabola is fine, or you can draw a slanted line that's just not as steep as this. So that would work as well. Okay, in the next section, we're going to look at a quadratic system. What that means is you're going to have two parabolas. And they have to meet the requirements beneath the graph. So here you want to draw two parabolas that have two solutions. So they're going to touch twice. In this one, you want to draw two parabolas that face in the opposite direction. Parabolas can only open up or open down. They can't open sideways. That would be a square root relation. So parabolas only either open upward or open downward. So in this graph, they have to point in opposite directions. You need one up and one down. Down here, you can see it in your book. It says one solution, same direction. So I'm sorry that it's covered up here. I can't, oh wait, I can get that out of my way. Okay, that's better. Okay, one solution where they open in the same direction. So two parabolas that open upward or two parabolas that open down. And then here, no solution. Doesn't matter which direction you choose to draw them, but they can't touch ever. Even if you extended them forever, they're never going to touch. So I'm going to ask that you pause your, and actually you can answer the questions below the graphs too, down here. So finish this page and then you can push play. Okay. Just to point out on this page, I now have two different examples. Here's the one with the vertical line that you could have drawn, and here is a horizontal line. That's at the top of the page. Quadratic systems. Here's one with two solutions, but here's an alternative where in this one they're pointing in opposite directions, but in this one they're pointing in the same direction. The difference here is that one A value is greater than the other A value. So the skinnier one has an A value that is bigger. The wider one has an A value that's smaller. So that would cause them to cross each other twice. Okay, one solution, opposite directions. Some people might draw the vertex as their solution, or again, we can kind of brush up against the side where these touch at one point. That would work as well. Same direction. If you drew something like this, it's really important that the A value is the same, meaning they have the same width. One can't be wider than the other one. It's kind of like parallel lines that have the same slope, then they would never touch. So this purple here is kind of like parallel to the purple here. They're the same distance apart at all times, and same with the blue is parallel to the blue, same distance apart. That would only happen if the A value is the same. And the last, no solution. If you had these pointing in opposite directions, then they're going to point away from each other and never intersect. The answers to the questions down here, can a linear quadratic have an infinite number of solutions? The answer to that is no. You can't have a line that touches every point on a parabola. And for this one, a quadratic, the answer is yes. You could have a parabola that's in standard form and you graph it, and then you take another parabola that maybe was written in vertex form, and at first you don't realize that it's exactly the same parabola. So every point is the same. Okay, so to graph systems on your calculator, you're going to need to have your calculator out. And let's clear your calculators so that it kind of resets everything and we can work fresh. I want you to click second plus. That'll give you this screen. You hit 7 to reset it. We're going to reset all RAM. That's 1. And then, yes, we want to reset it. That's 2. So second plus 7, 1, 2. If you want to write that down in your book, that's how you reset your calculator. If it's doing anything that you're like, I don't know what's going on, I don't know why this isn't working right, just hit second plus 7, 1, 2 and reset it. Okay. I'm going to show you what buttons we push before we actually run through a problem. So when we want to find the points of intersection or the solutions to a system, we first want to get to our calculate menu, which is above the trace button. So we're going to hit second, trace. And above the trace button, it says calculate. We use that button for a lot of stuff. And on that menu, we can find the zeros of a function, which are where the y value is equal to 0. Those are your solutions to one equation. So those are x-intercepts. Then the min, which is a vertex, that's a min. A maximum is a vertex, that's a max. And then 5 is intersection. We're not going to use 6 and 7, just really 2, 3, 4, and 5. So we're going to choose option 5, where they intersect. You can push the number 5, or you could scroll down. Then we're going to scroll close to the first intersection. Once we get there, we're going to hit enter, enter, enter. And your calculator is going to tell us the answer, or tell us the coordinates of that intersection. The coordinates are going to be written as inside of brackets. So once we get that first coordinate, I'm just going to use the 1 to tell us that's the x and y from the first point. That's going to be in our solution set. And If we have a second intersection, we're going to have to go find that second intersection. So we just repeat the process. We actually, if we have one intersection, we do this once. If we have two intersections, we do this twice. When we move on to bigger and better functions, if we have this 3 intersections, then we're going to do this 3 times. So, we're going to go second, trace, intersect. Option 5. And this time we're going to scroll close to the second intersection. It's just whichever one you didn't use the first time. And then once you get nice and close to it using the arrow buttons, you're going to hit enter, enter, enter. And actually, when you scroll close, you're using not the up and down arrows on your calculator, but the left or right arrows. The up and down arrows just switch the cursor from one function to the next, so that won't help you. Okay, so once you get the xy from the second point, we'll call that x2, y2. Once you know what it is, you write that in your brackets as your other solution, and then you close your brackets. So you write your solution in brackets. Your answer should be written like that. So let's do a problem. Solve the linear quadratic system by graphing. Round to the nearest hundredth if necessary. Hundredth, just so you know, is 2 decimal places. So if it's asking you to round to the nearest hundredth, if you had 2.345, that would be about equal to 2.3. We want to stop here, but we have to look next to it. If this number was 0 through 4, we would leave this a 4. But if this is a 5 through 9, we would round this up. So the 4 becomes a 5. And what I wrote here is about equal to. We kind of make a squiggly equal sign. So make sure that you round to the right place if you're asked to round. So let's do number 1 together. You're going to start on your calculator by hitting y equals and entering the equations. So negative x squared plus 5x plus 6. And y2 is just x plus 6. And now we're going to look at the graph. Okay, I can barely see this second intersection. I should still be able to scroll over to it, which is fine, but I'm going to change the window so we can see the whole thing. If you notice, I would like to see what's going on up here a little bit higher. So I'm going to increase my y-axis and make it taller. Go to the window, increase your y-axis by going to y max, and let's, I don't know, make it 20. See if that's enough. Good. All right, so now we're ready to calculate the intersections. We hit second, trace, intersect is option 5. It says first curve, we're just getting close to the intersection. So hit enter, second curve. We don't have to do anything for that, just hit enter and then enter again. And it tells us the intersection is at 0, 6. If you got something funky here like 0.000012, that's 0. If you are not sure, go to second table, and if you look, we see that 0, 6 is on the quadratic, the first function, and 0, 6 is on the line. Notice this row matches. These rows do not match. This one does. So 4, 10, and 4, 10 is going to be our other intersection. So those are our 2 intersections, is wherever the rows match. So 0, 6. want to write in blue. Okay. Is our first point. And then I know we already saw the other from the table, but I want to do it on the graph. Okay, to get to the other intersection, we do second, calculate intersection. Oops. Second, calculate intersection. And we use the right arrow to get closer to the second intersection. Hit enter 3 times, and we see that it's at 410. So this is telling me my solution is 0, 6, and 410. Okay, you can try the next one on your own. Pause the video, push play when you are done. Okay, for the next one, you should have gotten negative 1.47 and negative 3.77. Those are rounded to the nearest hundredth, and 1.81, comma 3.89. If you did not get that, then please try it again. And normally the first thing I tell people to check for if they didn't get it right is that when you type these in, that this here, you use the negative button, and this right here is a subtraction sign. Because when we write them, they look exactly the same. But when you're entering it on your calculator, you actually have to enter x squared plus 2x minus 3 using the subtraction. And then for the other equation, you have to use the negative button, which is down here. So even though when we write them, they look the same, when we graph them or we type them into the calculator, we have to think of negative and subtraction as 2 different things. So your graph should have looked like that. So if you didn't get those intersections the same, try it again. And the second one. There you go. Okay. So we're going to solve this system algebraically using substitution. What is the solution to the system of equations? If you notice, we have a quadratic and a linear. So this is a linear quadratic system. They both say y equals. This is the easiest type of substitution because when both equations already say y equals, you don't have to isolate either variable. So if, for example, you don't have to write this down if you don't want, but if this had said y minus x equals 3 instead of this, then we would have had to say, I either want to get y by itself or x by itself. And since y is alone here, I'd probably say it's easier to make this one say y equals. So we would add x to both sides, and then we would have y equals x plus 3. And then we would be able to use substitution and say instead of y, I'm going to use x plus 3. And that's what we do here. We say instead of y, we're going to use x plus 3. So we're substituting x plus 3 in for y. Okay, so in this problem, it didn't start out like that, so I'm going to get rid of that stuff. But in this particular problem, we are able to substitute x plus 3 in place of y and set these equal to each other. So this is going to look like this. X plus 3 equals negative x squared minus x plus 6. Now we only have one letter. So the goal here is to solve for x. And keep in mind what our answer should look like. We're trying to get the 2 points where this line and parabola meet, or it could be 1 point, or it could be no solution. Those are our options for a linear quadratic system. So we're going to start out thinking that we're probably looking for 2 points, but maybe it's just one and maybe it's none. So solve for x. Once we get our x values, then we would know this is where our x values are going to go, and then we can use that x value to solve for y. So I'm looking at this and I notice I have a negative x squared. I would rather, because we're going to solve this quadratic the way that we've learned how to solve quadratics in the past, and I just feel like it's easier to have an x squared that's positive. So I think we should add this x squared over to the other side to make it positive. And if you recall, solving quadratics, when you first learned it, you want to set the equation equal to 0 before you solve. And you might be able to solve by factoring, or you might be able to, or maybe it's not factorable and you can solve by using the quadratic formula. If you don't have the quadratic formula memorized, it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. These are the 2 most common methods used, but you do have the option, if you prefer, to solve by completing the square. Some of you don't like the quadratic formula, so you like to do completing the square. That's fine. However you are going to solve this, clearly we have a squared here. This is going to be a quadratic. So let's go back to the problem and see what our plan is going to be to get this solved. We're going to set this equal to 0. So I'm also going to add the x to this side, and I'm also going to subtract the 6 from this side. What that does is negative x squared plus x squared, negative x plus x, 6 minus 6, all of that equals 0. So on this side, I have positive x squared, x plus x is 2x, and 3 plus negative 6, or 3 minus 6, is minus 3. So that's it. Now you just have a simple quadratic that needs to be solved. Is this factorable? If it is, that's the easiest way to solve. So do we have 2 numbers that multiply to negative 3 and add up to positive 2? 2 numbers that multiply to negative 3 and add up to positive 2. So if you've got those numbers, you know that here we put x times x, because if we FOIL, we got x times x is x squared. So we're going to do 3 and 1. Which one is positive and which one is negative? Well, they add up to a positive, so the 3 has to be positive and the 1 has to be negative. So just to double check, 3 times negative 1 is negative 3, and positive 3 minus 1 is positive 2. So if you FOIL this back out, it gives you this. All right. At this point, when you're solving, you have 2 things multiplied together to get 0. This factor times this factor. Well, if you multiply 2 things together and get 0, one of those things has to equal 0. So we split the problem and we say either x plus 3 is equal to 0 or x minus 1 is equal to 0. One of those has to be equal to 0. So on this side, we minus 3, and we find out that x is equal to negative 3. For this one, x would be equal to positive 1. So what we now know are our x values. but we don't have our y values. So how do we do that? Well, we do that the same way we did with solving a linear system, which is plug these values back in and find y. So I'm going to do my work. I'm going to actually move up here and do this. So if x equals -3 or x equals +1, you have a choice of which equation you want to plug into to solve for y. To me, this bottom one, the linear, looks easier. So if x equals -3, then we're going to have y equals -3 plus 3. So y is equal to 0. When x equals 1, we have y equals 1 plus 3. So y equals 4. Now, we know that the -3 goes with the 0, and the 1 goes with the 4. And I'm going to put those into my solution set. But the very last step is going to be to check that these are right by graphing this. Now, you don't have to calculate the intersections on the graph if it looks like it's obviously right. But what we shouldn't see are two functions that don't touch at all. We shouldn't see two functions that touch only once. We should see a parabola and a line that cross at these 2 points. So let's just make sure that we see that. I'm going to move this over here. So y equals -x² minus x plus 6, and y equals x plus 3. Now on a test, I know on your homework, a lot of you won't take the time to check to see if this is right, but on a test, I would recommend doing that. So -3, 0. Let's zoom this in. If you want to reset the graph, because I changed that window, hit option 6. So zoom 6, and it kind of resets it back to a window of -10 to 10. So -3, 0, that definitely looks like it's at -3, 0, and then 1, 4. So that looks right. So yeah, on your homework, you might not graph them all and check them, but on your tests, you definitely should. Okay, so I would like you to do the following problem. Pause this and work through it and see if you can get the correct intersection, both graphically, so you can graph it first on your calculator and see what the solutions are, and then I want you to try solving algebraically like we did above and make sure that you get the same answers. So you want to make sure that the graphic solution is the same as the algebraic. All right, pause your video and work now. So there is the solution. Hopefully you got them right. If you didn't, you can type them into your graph again, see if you can find your mistake, but you're also welcome to raise your hand and ask for help. The next 4 problems you are going to work through. You can work together with someone in class. And the first 2 are a little bit easier. The last 2 are a little bit harder. And then you can do this work right in your book. So once you finish working through these, you can then go to the next page. The next page in your book looks like this. So you can solve these algebraically. If you really get stuck, you can at least get the solutions graphically. But what you notice, if you notice, these both say y equals. This does not say y equals, neither does this, and neither does this. So in order to graph them on your graphing calculator, you'd have to get them to say y equals in order to plug them in. So If you're solving algebraically, it'd be kind of hard to check graphically. You have to get y alone. Your other option to solve graphically, it's a little bit easier if you use Desmos.com. So on that calculator, you don't have to get things to say y equals. You type the equation in exactly the way you see it. You can type any equation in any form. It doesn't have to be in standard form. It doesn't have to be in vertex form. It does not have to say y equals. So give that a try. If you go to Desmos.com, number 4 maybe, and just type in negative 3x squared plus 49x plus y minus 192 equals 0, you're going to see that quadratic. And then x plus y equals 0. So if you're having trouble solving algebraically, then as a backup, just try graphing them and getting an answer. For the problems down here, you are welcome to just solve graphically, round answers to the nearest hundredth. That's 2 decimal places when necessary. That's it for today. So work through the problems on 11 and 12. Hope you have a good day.